Dear all, we are about to start, and my name is Maxim Panov, and it's my pleasure today to welcome Professor Martin Takáč at our AI seminar at TI. Martin has a long career in different areas of science, but his especially recent work on federated learning from the perspective of optimization, and I think that today's talk is exactly on this topic, and well, we will know something about compression and sketching, and everything will be second order, I guess. Yeah. Okay, Martin, please.
Thank you, Maxim, for introducing me. Before I start the lecture, I was not really sure about the background, so I prepared some introductory slides about many things. So how many of you know about federated learning? Hands up. So maybe like half. Okay. How many of you knew about reinforcement learning? So maybe we can skip those two slides. Okay, so let me start with some brief introduction about FL, mention some challenges. Then I will speak about some projects what we are working now at MBZUAI. And afterwards, I'll speak about the topic which I speak here, okay? And again, if you have any questions, please stop me, ask questions as we go. I like it much more to be interactive. Okay, cool. So basically, what's the motivation behind ML? And also you'll see different templates because I took the slides from different sources. Actually, this template is from Samuel Horvath. Actually, he's also running these FL seminars and so on. If you want to join, I can give you some links and so on. So basically, in the past, what we did, we had a computer, let's say when I was trying to learn ML for the first time, you can download some data, let's say MNIST. All you need is your computer and that's it, right? But we understand now that bigger data you have, the better model you can get. So basically now we are shifting this paradigm to basically having the clouds. You can have basically huge storage with a lot of data inside. And basically in this case, you can train these big models on these HPC machines and so on, or in the cloud, okay? And basically those models are pretty good because you train them with a lot of data. But basically what's happening now, people don't want to share data, okay? And there are like different basically rules. Let's say in the European Union is basically having this GDPR, which is really someone is pushing companies not to collect data from people, right? But you still want to train the model, but you can't get the data. Okay, so that's basically the biggest challenge what we have. I want to use data from all your phones. I want to train the model, but you don't want to give me the data, right? So basically, what can we do? And basically now is the federated learning going into play, that we can somehow try to train the models on the devices, on your phones, and then don't really communicate the data, but communicate the models. Okay, so that's basically one way how basically what we can do. So basically in this case, you are not doing this heavy computation on a cloud, but you do computation on the devices. Okay, so basically we can do some training on every single phone and then somehow communicate the models. And actually there are so many applications which is already in production, which was basically trained using FL. Let's say if you think about if you're Apple, you can think about this Hey Siri, or you can think about the typing. If somehow Google phones, let's say Android, sometimes you want to write, it gives you the next word prediction, right? Again, all those have been trained using this FL setting. Basically, you really just train the model on your phones, and somehow it works, okay? And again, this could be very good game changer for actually many applications. Think about healthcare. In healthcare, you think about hospitals like this, it's somehow very hard to share data. Actually, in USA, I was working on some project for with the hospital, and the only way we could collaborate was that if my student went to the hospital, sit behind some computer without internet access, And all he could somehow do is just type there, okay? There was no way for us to get data. So again, usually in hospital settings, it's very hard to get data. You cannot share the data because of all these concerns for the privacy. So there's no way we can share data. Actually, this kind of FL is called cross-silo, where you assume you really have only few agents. Let's say you have like 10 hospitals, right? And usually those hospitals, they can communicate quite fast. And usually all those computers can communicate anytime, but still you have only few hospitals. So usually we have different algorithms for cross-silo. And the second setting is called cross-device. In cross-device setting, we assume we have like maybe billions or millions of devices, which basically can someone try to participate in training the model. And usually the training basically is the simplest algorithm you can think of is as follows. The server, the master basically will send the current model to devices. Every device will use their own local data to do some small update to the model, to improve the model. And afterwards, they will share their new model to the server, who will do some kind of aggregation, right? That's usually the setting which we are thinking about FL. So there are basically 3 different steps. The server will send the model to devices. Each device will do some kind of small operation. Let's say I will do, a few gradient steps or a few Adam steps, doesn't matter. And then I got the new model, which I will send back to the server, okay? And what are the challenges to really, basically, we really want to go and do FL in practice? So basically, one of the challenges, which is, I think that maybe the biggest one, is the communication bottleneck. Because again, like when you think about you have your phones, you maybe don't want to send your models to the server if you don't have Wi-Fi, right? Because you don't want to lose all your data. For example, sometimes the models can have like 200 megabytes, right? If you just do 10 iterations, you already lost 1 gigabyte of your bandwidth, right? Of your data plan. So usually you need to wait to be on a Wi-Fi, right? And also sometimes you can think about, we can have different parts of the world which have a much slower connection. Some parts can have much faster connection, right? Again, that's basically all those different issues that you can think of. The additional one, which is the challenge, is that I can ask a question as a user. If I participate, will you see my data or not? Because again, if I have some sensitive data on my computer, and I cannot have this guarantee that you cannot discover my data just by me participating, maybe I don't want to participate, right? If you can steal my data. So again, you, in some sense, even though we currently saw the paradigm that you train on a device, maybe someone can still infer something about your data on your phone, right? And usually it's very hard to get some formal guarantees for the federated learning that it will work for sure, and no one can discover your data, okay? There are actually a few ways how we can make it much better. One is what they call this homomorphic encryption, which means I can send some data and I can encrypt. We can still maybe sum them together and so on, it still works, but they're actually very, very expensive because this will increase the size of the messages I have to send. Also different issue in FL is that when you train the model, what kind of algorithm do you use usually? If you train some machine learning model, or HDD or Adam, right? What are the assumptions in HDD? Usually we assume I will sample the mini batch randomly, right? That's usually what we do. We have data, we randomly shuffle them, and then choose a mini batch, right? So basically, we assume they're sampled from this distribution randomly. But is this happening in real life? Think about I'm the Google or Apple. That doesn't matter. I want to train the model, right? And we somehow discussed that when you train the model, let's say from the pictures on your phone, you can maybe participate only when your phone is on Wi-Fi and maybe also on charger, right? So most likely, your phone can participate at night, right? Because at night you're home with the charger on the phone, right? So this really means that at a given time, maybe it's like 10 a.m. No one from UAE or from Europe will participate, right? Maybe it's 10 a.m., so maybe people from China will participate. Now, let's say later in the day, people in China maybe already having the day, and maybe USA will participate, right? So in some sense, the stochastic gradient I will estimate will not be random IID. Because you can see that the mini batches I'm using depends on the time, right? So basically we're getting some gradient updates from some part of the world. So basically in some sense, we can understand that we have this, not really the homogeneous setting, but at a given time, I can have different updates being sent from different regions, okay? That's everything about if I have pictures of the buildings in China looks very different from buildings maybe here, right? So that's one of the challenges. Second one can be also that the data itself is different, okay? We have different distributions. So if you think about pictures from, let's say, I don't know, here, from outside, you have maybe mostly sand and so on, right? Pictures maybe in, I don't know, Slovakia can have much more green. So basically, the data have different distribution. Let's say when you have the same distribution for every device, doing few steps on every device and then taking the average is maybe fine. If you have very different data, this really means that the minimum for each data point can be somewhere else, right? Again, that's a challenge. Additional challenge, basically, which I see is that many times, it's a thing about the hospitals. You have all these, let's say, MRI scans and PET scans and so on, but maybe you don't have always labels, right? So maybe just doctor can see the scan, hey, this is cancer, I know where it is. But if you want to train the model, maybe you need to tell exactly where is the cancer, right? To really have that some good model for, let's say, predicting where is the cancer and so on. So again, usually we have limited labels. And you can somehow ask questions, hey, maybe I can pay different agents, I need to convince them to label the data, right? And they can ask questions, why should this be good, right? And again, in some sense, the whole FL is about both statistics, computer science, and also the economy. Because again, if I ask question, hey, let's train the model together, why should I do it? Imagine that every one of you is running hospital. And you can maybe train your own model locally, right? Maybe you can be happy. So why you should work with me, or all of us, why we should work together to build one model? Why? What do you think? It should be better, right? But what if I'm running SSMC here? I have enough data myself, right? I don't need you. Maybe I'm running this big hospital. I have much more data than you have, right? Yeah, it's from my side. So again, basically, in some sense, there should be all these incentives, like, why me, if I'm, let's say, I have maybe much more data than all of you together, why should I participate with you, right? And also, does it help me if I participate with you? Think about if I have a hospital, I have the bridge hospital, the bigger one, maybe my MRI machines are much more powerful, right? Maybe you're running some small hospital, and maybe you have like old generation of the imaging technology, right? So maybe your data is going to harm me, right? Where my data can help you, but why should it help you, right? So basically, there are so many different aspects of FL which basically people try to address. Let's say how to make sure that if we contribute, let's say if I go with you, I will maybe get some rewards for this as well. Or basically, if I collaborate with, let's say, Maxim, maybe we have the same kind of hospitals, right? So, but still, I need to understand the benefit I will have if I work with you or if I don't work with you, right? Again, there are basically so many challenges what people are thinking about when they speak about FL. And there are actually a few review papers I can point out if you want. You can read about all those challenges and some suggestions how this can be addressed, okay? But again, one of the issues, let's say, about this personalization, this is basically trying to predict the next word. Another question. Do I want to have one model or not? Imagine you want to have this app on every one of your phones, right? And in some sense, you start writing, let's say, the first few words, and you should get some predictions. What would you use as a next word? Question. Should I have one model or not? No, because again, do you want this model to be adapted to myself, right? So again, different basically issue is how to make sure I can still somehow train, but the final model can be sound different for me and for Maxim, right? Even basically when we speak English, we always use different way of writing, right? You also speak about, maybe we speak the same. You will speak to my son who is teenager, I'm pretty sure he will be using different words, right? So again, there are all those different issues. And again, maybe one question, what do you think why this next word prediction was basically one of the first applications of FL? What do you think why? Again, the next word predictions really was one of the first usages of FL in practice. What do you think why? Yes, there are a lot of personal data. You don't want to share the data because you're writing emails. You don't want to see the emails. But again, it was a good use case. What else? If I mess it up, who will die? No one. Just few buttons, delete, 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 right? If you think about like trying to train these models to find the cancer on your PET scans and so on, people can really die, right? If you don't find out. So again, usually those use cases are super easy and people can understand the limits and the issues and so on, but still it's not really serious if you don't get it right. Okay, that's fine, okay? Actually, one of the biggest issues in FL is actually robustness to poisoning. What does it mean? Let's say we want to say we are running the hospitals and so on, we want to collaborate. What if someone wants to hurt us? Think about this one. If I make your model wrong or bad, and I will not use this model myself, you will have better reputation, I will benefit, right? So basically, always when you can collaborate, there could be someone who wants to harm you. Because if I harm the whole process, and I know I harmed it, maybe I can just only use my own model and basically can completely screw up you guys, right? So again, basically sometimes in FL, when you think about this one, always when you want to collaborate, you maybe don't want to trust this data. Or saying differently, even maybe it's not really bad intention, but maybe the data which you have is from different distribution, right? So basically one of the main questions, actually we are working on this one with some guys from Germany and so on, is that if I have many agents, let's say the whole room here, it's not only I want to train one model, I also want to find out with whom I should collaborate, right? Maybe who has the same data from the same distribution as I have. And it's very easy to say that let's do it like this, let's find out if we have the same data or not. But remember, we cannot share the data. So question here, how can I find out who of you has the same data as I have from the same distribution? In this case, I know I want to collaborate with you guys if we cannot share data, right? It's pretty hard because I cannot see your data. All I can somehow do is maybe do some gradient computations. I don't know, right? But also I cannot see your gradients because if I see your gradients, I can really get your data to me, right? So again, there's so many challenges. And again, it's like still early on to have the good solution, okay? This already discussed that you can communicate on it sometimes. Yeah.
So what you see, like the sum of the gradient?
So again, imagine that I am some hospital, okay, hospital A. You're hospital B, Maxim hospital C, and so on, right? I would maybe pay you to compute gradients for me, okay? Think about the setting. I want to pay you, pay to Maxim. I want to pay everyone to compute gradients. But first of all, I have no clue if your data is beneficial for me. And also, you cannot send me the gradients itself because you don't trust me, right? So maybe we can have some entity, like government entity, which can get the gradients from you for different models, but somehow need to decide if this is going to benefit me. But how does it know? Because it doesn't have my data, right? So basically, like the way which we are working now on is using some kind of DFO on for the government to basically give me some different combination of the gradients and see if this is improving my validation data set, for example. That's one way. But actually, we are discussing different strategies. But still, in this way, if I find out that your gradients are not helping me, I know you have different data, for example. Let's not pay you for this work because I don't benefit from you, right? For example. But again, there are so many challenges that are not really addressed yet. There are some ideas, but there are no clear solutions yet, okay? And actually, different big challenge what we can think of is that you can have maybe different devices of different capacity, right? Maybe you have the latest iPhone. Which one is the latest iPhone? 14?
The last one, 14.
14, okay. So maybe you have a much more capable computer, right? I have maybe very old mobile phone. So maybe I cannot have these huge models inside, right? So basically now the question is how we can have multiple different devices which can collaborate. Maybe actually I have some small device where I cannot fit a big model. Maybe I have some good phone or good, I don't know, iPhone 14 where I can fit a bigger model, right? Still, the question basically would be, how can I build maybe multiple models which are somehow like nested and so on? Again, there are so many challenges not really addressed yet, okay? So really basically shifting from this old way of training where all the data was there to this setting, it still will take a couple of years, okay? But still we are moving to this way where the computation will be done on devices and you just share some weights, not even weights sometimes, only some small changes. Okay. So I will speak about the one application that we currently work in my team is basically how we can use FL and RL for smart grids. Okay. Think about this one. UAE committed to be net zero by 2050, right? I know I was just checking the audience if they know. but what? Yeah. So basically by 2050, we should be net zero emissions for CO2, right? And basically we are thinking, how can we achieve this? I think that UAE currently is building nuclear power plants, right? And maybe in 2030, 35 or 40, maybe 25% can be from nuclear, right? Maybe that's the current, my current information I have now, right? So basically, if we are thinking, how can we use reinforcement learning to maybe make the renewables much more better? Think about this one. If I put my solar panels on my roofs, okay, and maybe I have like 2 kilowatt, okay, generation power potential. What if at the morning we have maybe fog, right? How much I will generate? Almost nothing, right? But let's say if you are the producer of electricity in I'd say Abu Dhabi, you are maybe relying on my production, but you will not get it, which is very bad, right? So again, question would be here, how can I use maybe some AI to make this smart grid, let's say, or the renewable energy much more reliable, okay? It's not so like stochastic and so on. Again, we are going to use reinforcement learning. I think there was maybe like 42% of you who said you don't know much about RL. Just kidding. So basically, what is it in RL? You have environment, you have the agent. Agent will see the current state and can choose some action, okay? And afterwards, you will get a new state and some reward. And the goal of this game is to basically choose the action in such a way you're going to maximize some reward, okay? Cumulative reward from beginning until the end. And again, there is basically some transition. If you're in current state, you choose some action, you will get to just do some new state. There could be also some kind of randomness inside, okay? So basically, that's the RL. Maybe you heard about AlphaGo, or basically, like in this case, the AI will somehow manage to beat the world champion of the game Go. And you can see the progress from 2016. If you train this RL, you need to use some human knowledge and all those rules and so on. Basically, in a couple of years, basically in 4 years, there's this mu zero, which can actually beat the game, chess, all those games, and without any human knowledge, which is pretty impressive, right? So you can see that RL is getting much better to basically playing the games and solving different problems, right? And also in RL, you don't really, it's not really supervised learning. You don't tell to the neural network or to the agent, by the way, you should do this action. You don't. The agent just learns by playing this game over and over again, okay? Sometimes they even let play multiple agents against each other, right? That's also a way they can learn. So basically, let's now see how can I use this RL into smart grid. Let's focus only for now in this talk, only for some small houses which I can have. Maybe get house, I got some battery, I got different house, here's some battery, I got different house, there's a battery, they're connected to the network and so on, right? And question for you, if I want to do reinforcement learning, why? If you are the house owner and you have the solar panels and batteries, why would you like to do any decisions? Or what are the decisions I want to make? What are the actions? Charging the battery. How much I should charge the battery, right? Or how much I should discharge the battery, right? This is my action, right? What is my state? Carnival batteries, what else? Time of the day, right? The features, let's say, how much sun it is, do I have fog or not? Because again, all those things will influence my decision. What else? Think about this one. It's 8 o'clock morning, right? Will the optimal action for me will be the same as optimal action for Maxim, or basically for some teenager? Will the action be the same? The optimal action, not. Why? Because we have different consumption, right? So my optimal action depends on my consumption, right? For example, I have one household who is doing some business inside, right? So his consumption will be pretty large during the whole day because some people will come to his house to work. For me, 8 o'clock, I go to work, zero consumption, maybe the fridge only, right? For teenager, the consumption is very different, right? They are working the whole night and they fall asleep maybe at 5, 6 a.m. Nothing, they woke up at afternoon and so on. Very different consumption pattern, right? Very different consumption, very different demand for electricity, okay? So clearly, we understand that the state is very complicated, but for every different house, I have a different optimal policy, right? Very different. And also, basically, in some sense, the environment is very stochastic, okay? Even though I know it's basically currently 8 o'clock morning or 10 o'clock morning, how much I will generate in this 1 hour depends on different factors, like whether do I have now sandstorm or not, or snowstorm, doesn't matter. It depends where you are, right? So basically, it's very hard to predict how much I will generate. So therefore, basically, the optimal policy will be also very stochastic.
Selling energy for like selling energy.
Yes, you can also sell. Let's say that's actually one of the things what someone claimed that maybe I can think about myself. I want to minimize my cost. Maybe the government doesn't like that because maybe they have different objectives, right? So basically, if you think about, again, we discussed this one, when I just look at one house, maybe even my consumption pattern will depend on the weather outside. For example, if you are inside of the house, it's super hot, you will run your AC much more, right? So again, there are so many even features which influence my consumption. There are so many features that influence the production, right? Everything, okay? Again, we have fog or we have this one, we don't generate much, right? So basically, in some sense, if you think about it, I have many houses. Each house can train its own policy, the optimal policy, right? but maybe I would like to collaborate with you guys. Why? Why I would like to use federated learning to collaborate with you to learn a good policy? There's something common, right? Maybe the features, how they influence my generation potential is useful to share, right? Again, there are some parts of the data. Let's say I want to understand if I have this temperature outside, when I have this humidity, when I have this maybe hour of day, let's say, and also the month of the year, how much I can generate, right? And maybe this information, maybe we can learn together, right? So it's pretty cool, right? I want to somehow like collaborate with you to understand how different outside factors are influencing my generation potential, right? So again, in some sense, this is basically what I said. There could be some private knowledge, which I don't want to share with you. What is the private knowledge I don't want to share with you at all? My consumption, right? If you know I don't consume anything during the whole day, I could be easy target to get my house cleaned, right? Because again, if you know there's no one, yeah, let's go there to visit, right? So again, in some sense, you can see most important, how many panels I have, I don't want to maybe share. How much is my battery storage capacity? I don't want to share, right? How do I orient my solar panels? Maybe it's somewhat private for me. But the most important is my consumption, right? I don't want to share this one, because then you can somehow use it against me, okay? So basically, in some sense, if I think about having some kind of like reinforcement learning, tool, which basically I want to really just use in some FL setting, maybe there are some parts, let's say in this case, it's going to say that I will feed maybe the external features, the hour of the day, maybe the humidity, the temperature, and so on. Also with some kind of like my consumption, right? I want to feed this one to some huge neural network to get some optimal policy, basically how much I should charge the battery or discharge and so on at given time. And basically only some parts of this network, I want to somehow collaborate in this FL setting, right? Some parts, let's say, which can be representing my consumption levels and so on, I want to keep private to myself, right? Because I'll see that now we can see I can use this federated learning also with reinforcement learning to really just use some common knowledge which we can benefit, but still keep some private information only for me. Okay, cool. Now, what could be the reward? Because remember, in reinforcement learning, we somehow said we should have some kind of reward. Inverse of the cost. That's one good suggestion. If I am basically only myself, thinking about myself, I want to really just minimize the cost of my household, right? But again, we somehow said that the final bill can be one way. If something about the UAE, the peak of consumption is during the day, right? There's the peak. If you can produce the clean energy maybe by nuclear in a couple of years, 25%, right? You can maybe produce something from the solar panels, which are quite stochastic, but still we can produce. We can build some, let's say, wind turbines and so on. But what if the demand is much higher? What will happen? Imagine we are having 12 o'clock and all the nuclear and all the solar and renewables are not sufficient. What they will do in Abu Dhabi? Burn gas, right? You will burn gas. So basically, on different hours of the day, you can think about how clean the energy is, right? Maybe during the peak hours, we need to burn gas to produce more because we need more, right? So basically during the day, maybe in the middle, the energy which you consume is much more dirty. So basically, maybe if you have energy in your batteries, the optimal policy would be, hey, release them to the grid, right? You as a house owner say, why? Because I will give you some CO2 credits, right? I can give you some maybe Bitcoins or CO2 coins, doesn't matter. You will be rewarded by this one just to make sure that the energy which we have here is clean, right? So basically now you can see that if the government start to giving some incentives, the optimal policy will change. Maybe the optimal policy will be all the power I generate, I put to the grid during the peak hours. All the battery which I charge at the night, I put to the grid. At the night, there is not much demand maybe, and there's still 25% nuclear. I can charge the batteries. Okay, so now basically the optimal policy is different, right? Again, once you start having incentives, basically you're changing the reward, not just to be the bill I need to pay to the supplier, but also basically minus the CO2 emissions or CO2 credits I'm getting. Or basically, also one of the big issues I want to achieve is to stabilize the consumption in the grid, right? Really, what I really want to achieve is that the consumption now and one minute later or 30 minutes later will be roughly the same. So basically, there could be multiple different objectives which we can actually balance to have really the optimal policy for the whole economy, for the whole UAE, for example. Okay? Any question here? But basically what we see that in some sense to achieve this, we should somehow have the policy for every single house. How do I behave? How do I charge batteries and so on? Again, if you want to be greedy, there is no incentive from the government. You just really want to minimize your bill. But clearly, this is not really the optimal thing to do for the whole country, right? Yes.
Each individual part of the grid observers runs to state more observation.
Yes.
They're also sharing.
Again, you observe some kind of, let's say, features from weather outside and so on. You are sharing maybe this one, right? Again, basically, once you're training the model, you can say this is the shared knowledge I'm happy to share. Because in some sense, I'm trying to contribute to build a better model to understand how different features influence how much I can generate. Because again, one of the biggest issues of renewables is that you don't really understand for sure how much power you will get next 30 minutes, right? Or next hour. You don't really know. It's very stochastic. Let's say if you see the pictures from Germany, I was actually reading some paper. They showed that say one day it was perfect. Second day, there was basically some clouds. So 20 or 30 minutes, my production went to 25%. If you compare with the previous day when it was sunny. So basically, if you think about, actually, also in Slovakia, we have these huge, basically fields with solar panels. I get clouds, all of them are gone. And it's like 25% can drop from, let's say, 1 gigawatt to 0.25 gigawatts. It's a huge drop, right? Actually, in Czech Republic, I was speaking with my friend. He's actually the head of the research for one of the biggest energy generating company. He said they're putting thousands of cameras facing up just to start building the good models, how the clouds are moving and so on. Really, they have thousands of cameras facing to the sky just to understand what's happening. Imagine this one, that thousands of cameras just seeing the clouds and, but still they need this one because again, it's an issue that you have this stochasticity, you want to understand, you want to limit so you know what you can get roughly, right? The same basically here. Therefore, basically I'm saying that if every house will put some kind of camera facing sky, you maybe want to build this shared knowledge, how much I can generate at given features, right? Okay. Any other question about this part? Because now I basically want to address the main title of the talk. I got 20 minutes. Maybe rush a little bit. But again, we can also skip a little bit. Okay, so basically, let's be somehow thinking about the settings which I want to address here. I got a bunch of devices. Capital K will be number of devices. Every one of them can have some local data. So basically, I will denote by Fj the cost of, or the value of the function, the cost function for each of these devices, okay? Basically, in the FL setting, I want to maybe minimize this one, okay? That's basically one way. You can also put some basically different parameters we want, but that's the easiest setting, okay? And each of them can communicate with the server, right? I can send function values, gradients, and so on, or the weights. Okay. Again, for simplicity now, I will assume all these devices can always participate, think about hospitals and so on. They have very good servers and so on, we can communicate, that's fine. One of the basic algorithms, actually it's state of the art, is called FedSGD. In FedSGD, basically what's happening, the server will send the current model to devices. Each device will compute gradient. I will send the gradients to the server. It will compute the sum or the average of them, and I will update the weights. What is bad about this? It needs many, many iterations, right? You can imagine SGD. How many epochs do you run SGD for? 10 epochs? Think about 10 epochs, right? Imagine I will have maybe some small mini batch. Maybe I will need to do 1 million iterations per epoch. It's 10 million iterations. Every iteration here, basically, I need to send the gradient, right? Imagine a small model size, 200 megabytes. How much time will spend waiting? A lot, right? Actually, I was doing this computation actually this week or last week in my class. We said if I have 14 servers, I will take ImageNet. I will have only 1 gigabit connection. 21 days per 1 epoch, he will communicate. 21 days. And this is the clever communication in the tree structure, right? 21 days just communicating, which is basically the main bottleneck here. You can think about, hey, maybe I can use some kind of compression to make this one much better. Okay, you can do compressions, of course. I will explain what is compression. Do we know what's compression or not? In Federated Learning. Okay, I will explain this. Basically, I will explain a couple of slides. Okay, but still, like one of the main issues in this talk could be thinking, how can I decrease the communication even much more? Okay. Again, HDD is awesome, but if I can decrease the communication not from million to 500,000, but maybe from million to 10, it'd be awesome, right? So this is the compression. Compression is some function. In this case, maybe it's a random function, which takes the vector x or number x. I will produce maybe less bits. Okay, think about this one. If I have a number from 0 to 1, right, is a float. I need to store how many bits? 32 bits, right? I need 32 bits to represent a number from 0 to 1 in a float, right? Maybe I can do a compression, maybe a random compression, where I just need only 1 bit. Imagine this one. I want to have only 1 bit to tell you what is the number. It's crazy, right? Remember. So basically, in some sense, this can be a random compression, which means that the expectation of this compression of some input x will be the same x, right? If I have this random compression, maybe if I have this huge gradient, it's a d-dimensional vector, every number is a float, I need to send 32 times d bits, right? If I do this compression, I will send only d bits. So I can somehow be 32 times faster in terms of the data, right? Okay, so actually, how this can work? Imagine I get number x from 0 to 1. Could you design this compression? What should be the function c, which can be a random function? I don't care about this. But such that c of x is any number from 0 to 1, I will just produce only 1 bit, right? Let's say I will produce 0 or 1. Yes. Exactly. So basically, what you can say, this is a random function. Let's say if I feed 0.75, I output 0 with this chance, I output 1 with this chance. The expectation is 0.75. So basically, many times what people try to do to decrease the amount of communication, I will use some kind of compression like this. Maybe it's what I can do, I can take the vector x, I divide by the infinity norm. I get now from -1 to 1. I will send 1 bit for the sign. I will send 1 bit like this random stuff from 0 to 1, right? So basically in this case, you can say I can take this huge vector. I will send only 2 bits per dimension. So let's say if I had floats, which was 32, I will send only 2 bits per dimension, right? Which is pretty nice. But the most important thing is that this expected value, but the variance or second moment, we can now show that there's some omega, some number, some constant omega for different compressors. The variance of this one is bounded by the size of the input. This all makes sense because as I said, you take the vector x, divide by the L infinity norm, and so on. Yes? That's exactly quantization. This quantization. Actually, there are many different compressors. Yeah. So there are many different compressions. There can be bias compression. There can be like many things. I want to keep this one simple. So basically, quantization is basically one of the simplest things you can think as a compression. But of course, there are many different ways which are much better. Okay. I just want to keep this one very simple. Okay. So actually, because again, I want to speak about the second idea, which is much more important. How can I decrease this number of iterations from millions to only few? Because I think that's much more important. Decrease the amount of communication from millions to only few iterations, because then I can really save the communication cost. So there's this nice paper from Peter and his group. Peter is basically my former advisor, is in KAUST, which basically they call it FedNL. Again, if you think about, I want to really decrease amount of communication, maybe using just gradients is not sufficient. Maybe you can somehow use Hessians, the second order. Usually, you know, if you use classical gradient descent, you'll need a lot of iterations. Something, let's say, if for strongly convex and smooth function will be almost like kappa times log 1 over epsilon. Well, depends. It depends on the functions. If you just use Newton method, maybe you just need 20 iterations, right? So basically, one of the idea how to make it much more efficient computationally or communicationally is to use Newton method, right? Because if you use second order methods, you are using much more information, and therefore you will need only few iterations, okay? So basically, this is the high level idea. I compute Hessian on every single machine. I send the gradients from every single machine. I send the Hessians from every single machine. You compute the average of the Hessians, compute inverse, and then multiply by the gradient. That's the Newton direction. This algorithm will need only few iterations to converge, right? Do you see any issues there? A lot. What is the communication cost of this? Yeah, not even transmitting, even computing Hessian, even storing Hessian is huge. Okay, so clearly we cannot afford to run this one. Nevertheless, there is still this paper because they used few tricks which are pretty awesome to make this one somehow happen much better. Okay. So basically, what they somehow did, they said, okay, what if I choose some initial estimates of the Hessians, or maybe it can be identity, it doesn't matter, right? In this case, I don't need to communicate anything. If this is a random, from some random seed, I can generate on device, I can generate on server, right? I don't need to send anything. And then every iteration, every device computes the gradient. Okay, if you understand, you can do this one. Can maybe also store and compute the Hessian on the device. I'm questioning this if this is possible, but they assume you can do it. And afterwards, the device will send the gradient as before, so this is okay. Will compute difference between the Hessian and the estimate of the Hessian locally. I will do compression of this one on device. I will send this S to server, okay? And you can do different compressions for matrices because these are metrics. Let's say one of them could be, I will take the rank 1 approximation. Rank 1 approximation basically will be just one vector and one number to send to server. Okay, I can do it maybe. Depends on the compression. I can do this, I can send this message to server, okay? And afterwards, I will use this message to update my local estimate slowly. On the server, you receive all those messages for the Hessians. You receive the gradients, you make the average of them. And afterwards, basically what you can do, you had the estimate of some Hessians on the devices, and you will do the Newton step. Pretty awesome. They have pretty nice theory. They can somehow show you the convergence, quadratic convergence locally at the end. It's pretty nice. So again, we have very nice convergence. You need only few iterations and you find the optimal solution. Again, can I store the Hessians on device? Think about this one. I have my phone. I don't know where it is. How much memory do you have on the device, on your phone? How much RAM you have? Free RAM. You have 30 gigabytes. I got two left, right? I got 2 gigabytes left on my device. The RAM, okay? RAM. Only few, right? Now think about having some simple model, only 50,000 parameters, which is nothing, right? 50,000 weights parameters is nothing. The Hessian is already 4.6 gigabytes. Remember, I need to compute the Hessian, also need to compute and store this estimate of the Hessian. So clearly, I cannot run this method on small devices. I can't. Yes, question? Okay. How much time do I have? 5 minutes.
Okay, you might have 10 because the start is
No, that doesn't matter. Basically, the main message of this paper is to see how can I make this algorithm really able to run in practice. So basically, what someone want to say is that, you know, I cannot store the Hessian estimates. I can't. I cannot even transfer them. Doesn't matter. So I cannot do this one. So we decided to store some estimates of the Hessians on cloud. Cloud can store gigabytes, terabytes of data, okay? So in a sense, I want to shift the storage requirements from devices to server, okay? That's the whole message. And afterwards, I will not compute Hessians. It's impossible to compute Hessian on device. But something else I can do on devices. If you do PyTorch, you compute gradient. Do you know I can compute Hessian-vector product with the same cost? Again, think about this one. If computation of the function value takes 1 second in PyTorch, computing gradient takes 2 seconds, right? It's roughly twice the cost. Once you compute function gradient, now computing Hessian vector product is just additional 2 seconds. Okay? So really you can compute Hessian vector product without forming the Hessian. Really, I can compute Hessian vector products in PyTorch with the same cost, the same additional cost as computing the gradient, the same cost. So at the same time, everything is roughly the same without storing the Hessian. So basically, the main idea here is to use sketching and quasi-Newton updates to build estimate of the Hessians on server, where on device, all I do is multiply Hessian times some vector a few times maybe, again, in this smart way. That's the whole idea here. So basically now I can really skip all these updates and so on, but really now the server will send only some few vectors to device. Device will do this gradient computation and will sketch the Hessian. And then I will try to do some compression of some messages from server and the one I computed locally. And afterwards, I can use some kind of quasi-Newton updates to build good estimate of the Hessian on server. I will have the same guarantees, only a few iterations. But now this algorithm, you can implement even for phones. You can do it now. Before you couldn't, because you couldn't store the Hessians. Now on device, we only compute gradient and we sketch the Hessian a few times. That's it. So basically now this paper is making this FedNL really implementable in practice. I have the same guarantees and so on. I can prove the convergence, global convergence. I can do almost everything. That's basically the whole highlight. Okay. Any questions? I was rushing a little bit, but I think that I hope you got the message. If I want to cut number of communications, I cannot just use gradients. Maybe I need to use higher order methods. FedNL, awesome paper, they show how to do it, but it's not practical because you need to store Hessians on devices. You have to communicate some kind of sketched Hessian, not sketched, compressed Hessian estimates and so on. So in this work, we try to move the storage requirements from device to server to the cloud. But now actually this one can really run on your devices. It's only small additional overhead. Again, computing gradient, 1 second. I need to do additional 1 second or 2 seconds, right? Okay. Yes.
How do you exactly generate this ST?
ST are sketched matrices of sketch vectors. You can just generate them from Gaussian vectors or unit sphere. It doesn't matter really. There are multiple strategies what you can do. Again, we are now writing the paper, actually the second paper. In this paper, we just sketch them by choosing uniformly from the ball, from the sphere, sorry. So they're random, yeah, so that's pretty easy. Actually, there's some recent paper from Nestero, which basically show that maybe we choose ST to be somehow maybe related to the maximum eigenvalue of the Hessians or Hessian differences, can be much better. So we can do power method to maybe estimate those vectors. In practice, it shows it's much better. So.
But for the theory, what do you require from that? Do you require some, I don't know, L2 Frobenius norm, these ones or something?
Again, for the theory, we don't. But the theory is somehow, again, almost like for every quasi-Newton method, the theory is somehow better, it's somehow worse than gradient descent.
Yeah.
So the same what we have as here. In theory, in the worst case, this method is much worse than gradient descent. But in practice, it's awesome. Yeah, that's usually even for LBFGS, you have theory which is pessimistic. You implement 10 iterations, I'm done, right? Or 20. So it's the same here. You can't really show much more. Now we are trying to work on this from the recent paper from Nestero to see if we can use these new proofs and so on to make it better. So we have some results, and Artem is working on this, but now he went to see his girlfriend somewhere. He can go to Russia, right? Artem cannot go to Russia now.
Probably can, but whether he returns.
He doesn't want to go, but yeah.
Okay.
But again, in some sense, maybe in like 2 weeks or 3 weeks, we should have the paper out.
Yeah, it's very interesting. I was asking because in completely different application for computing some like central limit theorem inspired uncertainty estimates for neural network, like you treat neural network as nonlinear models, and you apply kind of a delta method, and you can propagate uncertainty like basically linearizing. And for that, you need to compute a Hessian as well, and you can do that. Well, not Hessian, Jacobian, but
yeah. Okay.
And eventually. And what we did, we tried to do such sketching which preserves certain norms and so on. So there are some methods which do that. I'm just curious whether it's also applicable here. It can be made some use of it. Yeah,
actually, one of the like different projects which we have now is to maybe use the same ideas here. Let's say I want to solve the Newton system, right? And the question basically is like you can use these quasi-Newton updates, or you can use CG. Conjugate gradient. So basically now we are working on some project where we want to use conjugate gradient, with the preconditioning, so precondition conjugate gradient to make it faster, actually precondition basically will be used by quasi-Newton updates. So you can really combine quasi-Newton with CG to build something sensible. And it's working very in practice. Again, the theory is still fishy a little bit. Because again, once you have quasi-Newton, the proofs are not so beneficial. But in practice, it's working much, much better. So yeah. Still work in progress, right? But still, it's nice.
All right, colleagues. I think we can proceed with questions and probably we already have quite a few.
Yeah.
Yeah, but probably any more questions?
Again, those papers, yeah. Those papers should be on archive already. So actually this one is on archive for sure. Let's see, we go to my website, Takáč. So again, if you check my name, the first letter of my first name, my surname @gmail.com. The first paper is there for sure. The second one we submitted to this higher order methods for NeurIPS workshop. That one should be somewhere ready, I think, or maybe it's already on my website. Again, but if you want to do my first name and surname.com, mtakáč.com, this publication, yes, this publications, you can see the papers there. Okay, again, the theory, we have like different proofs inside. You can really check it out. But actually, the experiments are pretty awesome. Actually, I have the experiments here. The results. So many slides.
But the papers on the website are updated because news are not updated for a year and a half.
The papers are different. I have some small script which basically always modify my website and so on.
Okay.
So you can see this one is here. This one is the FedNL. And why? Because this communication, right? FedNL, you need to communicate a lot. In our case, which is this, let's say the truncated, we have multiple different updates. But you can see this one is much better because we just do some small sketching and so on. You can see again, if you have some easy problems, again, do you know this A9A data set? You have 119 features. There's nothing, right? I can store the hash on that's like 1 megabyte, not even 1 megabyte, it's nothing. So for this one, FedNL, awesome. It's pretty good, right? You can store in the hash on, it's nothing, doesn't cost you anything. But once you go to larger data sets, with basically maybe like 10,000 or 5,000 features already, FedNL is pretty slow because they need to send all this huge stuff, right? Where our stuff is much better, okay? It's much better. So again, there are multiple different data sets. I don't know the dimensions from the top of my head, but this is in thousands. And now you can see that FedNL, even though they have not nice theory and so on, but still storing the hash on device doesn't work, but still they need to somehow send much more data to make it work. Okay. So also we have some experiments which are pretty cool. FedSonia is actually, Sonia paper is my paper. Actually, Sonia is my daughter. And I was having a student and his daughter was born and her name was Sarah. So he made algorithm Sarah.
And also it was Marina somewhere around.
Yeah, but he made the Sarah algorithm, my wife. When will be the Sonia algorithm? I say Sonia. Stochastic Newton, inexact. So okay, let's do this algorithm. So again, like my wife influenced my research direction. You can see it here. This will be Newton, so Sonia, stochastic, Newton, inexact. I don't know. You don't need to be the person. Yeah. So my students actually, they make this Sonia algorithm. And actually this one is the Federated Learning version of Sonia. In Sonia, basically what we do, we are building some kind of like interpolation between quasi-Newton and gradient. So you are sketching the Hessian, building some special quasi-Newton updates, And also on some subspace, you do Newton step. On the different subspace, you do gradient descent. So the interpolation between gradient and Newton. And then they made the Federated Learning version of this one, which is the red ones. This is the FedNL, which is the paper from Peter. It's some expensive and so on. And then we have different versions of our algorithm. Okay, but still usually those works very nice.
Just like a question of the
Yeah.
learning, when you mentioned this issue.
I mentioned many issues.
Yeah, like the non-IID
Yes.
problem, but like because of the time shift cross country.
Yes.
But it's like IID modulo time. So is there like
It's still not IID really, because also like every device has also different data. So it's basically also heterogeneous, right? Think about this one. Think about people taking pictures of the food, right? The food in States look different than food in, let's say, Asia, right? So therefore we have different cuisines. Food in Italy looks different than food in Slovakia, right? So each device have data also from different distribution. That's the real world, right?
given time we can almost assume it's like IID.
Also in given time, you can have Africa and Europe, right? So
Like mixed together into distribution.
yeah.
Like that, but I don't.
It's again, I don't have answer for all those challenges. I just basically, Maxim said, maybe I can also make some small introduction to FL, just to put some challenges for you so you can solve them. Yeah.
Okay, I think you had pretty many questions.
Which is good.
During the talk, and thanks a lot, Martin. Thanks for coming, and hope to see you soon again.
Again, and we are not so far away, right? So
Yeah, exactly.
my first time here, I was impressed.
Okay, let's.
Thank you.